Okay, let's now look at this question here. A slab of copper metal of thickness B is inserted between the plates of a parallel plate capacitor as shown in the figure. The separation between the plates is D. If B is equal to D by 2, then what is the ratio of the capacities of the capacitor after and before inserting the slab? Okay. So before inserting the slab, this was the case, correct?
So I'm not able to see your screen.
Oh, I'm really sorry.
Yes, sir.
Just a second.
Yes.
Yeah. Are you able to see the screen now?
Yes, sir.
Yes.
Yeah. So I'll repeat the question. A slab of copper metal of thickness B is inserted between the plates of a parallel plate capacitor as shown in the figure. The separation between the plates is D. If B is equal to D by 2, then what is the ratio of the capacities of the capacitor after and before inserting the slab? Okay. Now, if you see, before inserting the slab, so this is before inserting the slab. Okay. Before inserting the slab, of course, the area of cross section, let it be A, and let's say the distance between the plates be D. Then what will be the capacitance of the parallel plate capacitor? What is the expression for capacitance of the parallel plate capacitor? C is equal to epsilon naught divided by D. Am I right?
D. Yes, sir.
Yes. Now this is what happens before inserting the dielectric. Not dielectric, this time it is a metal. Okay. Now after insertion, let's see what happens. So this spacing is D, no doubt about it. But for half the space in between the capacitor plates, we are not inserting a dielectric, but what we are inserting?
Metal.
A metal. Correct. Okay. So this distance is B. And B is given to be D by 2. Okay. Now in that region, on the left side, you have metal, and then on the right side, you have air. Correct. Now we had already discussed in the last class, when you have a metal inserted in between the capacitor plates, you already know what is going to be the electric field inside the metal. Inside the metal plate, what is going to be the electric field? Electric field will be 0 inside the metal plate. Metal plate, inside the metal plate, electric field is going to be 0. Now, the capacitor is going to be active only in the remaining region. What is the remaining region? D minus B. Therefore, what is going to be the new capacitance this time? After insertion, the capacitance is going to be epsilon naught A divided by D minus B. Do you remember seeing this formula? For metals, I had given you this formula.
Yes.
Yes.
Sir, will it not be P again, sir, since it's D by 2?
Yes, Rahil, can I not hear? I'm not able to hear you.
Sir, like, will not that D by minus P will be like D by 2 only?
Yeah. D minus D by 2 it will be. I'm going to write in the next step. Is this what you're saying?
Yes, sir. So it'll be D by 2 again. So will it
Yes.
not be P again, kind of?
It will be D by 2, correct?
Yes, sir.
Yes, Rahil, that's correct. So this D by 2, the 2 in the denominator of the denominator goes to the numerator, correct?
Yes, sir.
So the after capacitance is going to be equal to 2 times epsilon naught A by D, correct?
Yes, sir.
And before, let me call it as B, CB. CB is equal to epsilon naught A by D. So they have asked you the ratio of the after and before. First you should write after. Then you should write before, right? So after, what is this one? That is 2 epsilon naught A by D. The whole thing divided by epsilon naught A by D. So what gets cancelled? Epsilon naught A by D cancels. Therefore, what do you get? The ratio as 2 divided by 1, or in other words, 2:1 is going to be the ratio of the capacitances after inserting the metal compared to before inserting the metal. So the right answer is second option. Is it clear to everyone?
Yes,
Yes,
sir.
sir.
Yes. Okay. So one of you can explain. Go ahead. Anybody?
Sir, can you explain again?
Okay. So you have a parallel plate capacitor. What is the capacitance of parallel plate capacitor? Tell me, Rebecca.
Epsilon naught into A by D, sir.
Yes, epsilon naught A by D, correct. Now I'm going to insert a metal which is going to occupy a distance B, let us say, small b. Then we know that we have seen earlier in one of the earlier classes where whenever you insert a metal, what is going to happen is the electric field inside is going to become 0. Therefore, the capacitance will be primarily because of this region. So the formula for your capacitance in case of a metal inserted inside a capacitor is going to be given by capacitance equal to epsilon naught A divided by D minus B. All right.
Yes, sir.
Yes.
Okay. So what happens is epsilon naught A by D minus B will be the formula for when metal is inserted. So in this case, what is going to happen is B is given as D by 2. So you substitute D by 2 here in place of B. So D minus D by 2 is D by 2. This 2 goes to the top. So it becomes 2 epsilon naught A by D. Now we want the ratio of this one. Let's call this a second equation. This is first equation. Then 2 by 1 we want. Second equation divided by first equation when I do, it is C after divided by C before, which will be nothing but the ratio of the 2 epsilon naught A by D will cancel. So it is just 2 divided by 1, or the ratio is 2:1. Is it clear now, Rebecca?
Yes, sir.
Yes, okay. One more way you can understand is whenever, suppose dielectric is introduced, right? Suppose this is a capacitor. Let's say we have a dielectric constant K introduced between the plates. Then what is the formula for capacitance in that case? You know the formula, right? Epsilon naught A divided by, come on, tell me.
D dash minus T into
Yeah,
plus
D minus
T by
T plus T by
K.
K, correct? Okay. Now, if this is a metal, if this is not a dielectric, but this is a metal, then in the same formula, if you see, then for metal, the dielectric constant is infinity. Okay. For metals, the dielectric constant is infinity because it is a completely conducting. So denominator will be infinity. So what is 1 by infinity? Or T by infinity will become 0.
0.
Therefore, it will become epsilon naught A by D minus T. So instead of T, you have B here. That's all. Are you able to understand how this formula comes? Another way of
Yes,
looking
sir.
at it. Yes. Okay. Fine. So you can take it down. I'll give you a minute to take it down. Please take it down and then tell me once you're done. Then we'll go to the next question. Any doubts are there? Just let me know. Just a second. And now we'll look at the next question here. I hope you're able to see the question. Yes.
Yes, sir.
Yeah. So the separation between the plates of a capacitor of capacitance 2 microfarad is 4 millimeter. Initially, there is air between the plates. If two dielectric slabs of same area of cross section as that of the capacitor and thickness 2 millimeter each and dielectric constant 3 and 5 respectively are introduced, then what will happen to the capacitance? So if you see, okay, the separation between the plates of a capacitor of capacitance 2 microfarad is 4 millimeters. So case 1. Or you can say initially. Initially, simply the capacitor is there. What is the distance between the plates of the capacitor?
Four
Given
millimeter.
the question, yes, it is 4 millimeter. So distance of separation between the plates of the capacitor is 4 millimeter. And let's say the area of cross section of the capacitor is A, this area. Actually, it's a 3-dimensional, right? We are just looking at the cross section, correct?
Yes, sir.
Yes. Now, what will be the formula for this capacitance? Simple one. Inside you have dielectric, right? No dielectric. You just have air. So what is the capacitance going to be?
Epsilon naught A by D.
Yes, epsilon naught A divided by D, where D is equal to 4 millimeter, correct? Now what we are going to do, case 2. And this capacitance is given. What is this capacitance given as in the case 1?
2 mu Fahrenheit.
2 microfarad. So that's given in the question. So this you can note it now, right? Now in the second case, what are we doing? We are having the same capacitor with the same distance of separation of 4 millimeter. Same area of cross section A. But what you are going to have is not one, not air in between, but you are going to have not one dielectric, but you're going to have two dielectric slabs. All right. So you're going to have half this length with one dielectric, right? Of dielectric constant. How much is the dielectric constant? 3. Half the length, which means one thickness is 2 millimeters given. So this length is 2 millimeter. On the other part, it is not air. Other part is also dielectric. But not the same dielectric, a different dielectric. You're having a different dielectric, same distance 2 millimeters. Correct? Now, what is the dielectric constant in this case?
5.
5, correct? Okay. So now what is going to happen to the total capacitance? Right? That's what is asked in this question. See, the way you can solve this question is, we don't have a direct formula for this because we only have for air-filled capacitor. Next thing we have is what? Completely filled dielectric, but only one dielectric, correct? Third formula we have is, you have the capacitor, one dielectric is there, but not fully, but it is there only partially. Those 3 we have formula, correct? But we don't have a formula where both dielectrics are going to be there in the same capacitor, correct? Now we will derive it. Are you ready?
Yes, sir.
Yes.
But a very simple way we will derive, right? I'll tell you how you can consider this. Split this up. This is equivalent to having 2 capacitors like this. The length is 2 millimeters each. Area of cross section is A. Okay. One capacitor like this, having a dielectric constant of 3, and another capacitor like this, having a capacitance of 5. All right. Now I want you to find out, do you understand what I have done?
Yes, sir.
I have just split the capacitors like this, correct or not?
Yes, sir.
Yes, and return it as 2 different capacitors. Now individually you know what to do for them, right? Let's say this is C1, okay? Can you tell me the formula for finding the capacitance of the first capacitor, which has dielectric constant 3? What is the formula? Come on. First one, where the dielectric is fully occupying. Yeah, Rahil? Yes, tell me, Rahil. I couldn't hear you. I missed your voice. Yes, anybody, tell me.
Epsilon naught K into A divided by D.
Excellent, Akila. So let me call it as K1. Okay. So what will be your C1? Epsilon naught into what is K1?
3, sir.
3 into A by B. Correct. Now let's look at C2. Yes, Rebecca, tell me what is the capacitance of the second capacitor? What is the formula?
So it's epsilon naught into K2 into A by D.
Yes, ma, very good. So that's nothing but epsilon naught into what is K2?
5
into A.
5.
A
Very
by
good.
D.
Yes. D is same. Of course, in this case, D in both these cases is what?
Same, sir.
2.
2, not 4 millimeter, but 2, correct?
Yes, sir.
Yes, sir.
Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now tell me one thing. What is epsilon naught into A from this? 2 microfarad into D, correct?
Yes, sir. Yes,
I'm
sir.
taking this D here. I am coming to the first formula. What is epsilon naught A? It is nothing but D into 2 microfarad, correct?
Yes, sir.
Yes, sir.
2 microfarad into what is D? Can you tell me what is D in the original plate?
4.
4 millimeter. So what is it going to be?
8.
8 micro units, correct or not? 8
Yes, sir.
microfarad into 1 millimeter. Correct?
Yes,
Yes,
sir.
sir.
Yes.
Yes, sir.
So now I'm going to substitute that for epsilon naught into A. Okay. So can you tell me what is C1 now? 3 into epsilon naught A divided by 2 millimeter. Correct or not?
Yes, sir.
Yes, sir.
Yes. What is C2?
5 into epsilon naught divided by 2.
A by 2M.
Exactly. Right. So what is C1 going to be? 3 into, I told you what is epsilon naught. What is epsilon naught?
8
8
microfarad
microfarad.
into 1 millimeter.
8
1.
microfarad into
1
1
millimeter.
millimeter divided by 2 millimeter.
2
Correct?
millimeters. Yes, sir.
So what gets cancelled? Millimeter I can cancel. 2 and 8 I can cancel. It becomes
4.
4.
Therefore, C1, can you tell me what is it going to be?
12 microfarad.
12 microfarad, exactly. So this is going to be C1. Similarly, can you tell me what is going to be C2?
20 microfarad.
Fantastic. So 5 into 8 micro divided by 2. So this is going to cancel 5 into 4. So the C2 is going to be 5 into 4. That is 20 microfarad. Excellent. Are you clear about this?
Yes, sir.
Sir.
Yes.
Okay. Now, can you tell me how are these two capacitors connected?
Series.
Series, absolutely,
Series.
right? So that's all. So our sum boils down to just finding out what is going to be the capacitance when two capacitors are connected in series. What is one capacitor capacitance?
12.
Another one?
20.
20 mic.
Yes. So how do you find the equivalent capacitance? 1 by CS is equal to?
1 by C1 plus 1 by C2.
That's all. So it will be 1 by 12 plus 1 by 20. Correct? 60 is the LCM. So this will be 5 and this will be 3. So it is 8 divided by 60. Correct?
Yes, sir.
Yes, sir.
So CS will be reciprocal of this, so which is nothing but 60 divided by 8. If you divide by 4, right, or divide by 2, this will be what? 30 divided by 4. Or in other words, if you divide by 2 again, so you'll get what?
15 by 2.
divided by 2, correct?
Yes, sir.
So it is 7.5 microfarad. Let's look at the options. So which is the right answer? Second option is the correct answer. So are you able to understand this?
Yes, sir.
Okay, let me
Yes,
tell
sir.
you again. Let me just explain this again to you. So separation between plates of a capacitor of capacitance 2 microfarad is 4 millimeter. That means the normal capacitance is there. The distance between the plates is 4 millimeter. Epsilon naught A by D is going to be your capacitance, and that's given to be 2 microfarad. Now what is happening is, initially there is air between the plates, correct? If two dielectric slabs of the same area of cross section as the capacitor and of thickness 2 millimeter each, and dielectric constants 3 and 5 respectively are introduced in between the plates. Total distance is 4 millimeter. 2 millimeter, you are inserting one dielectric, another 2 millimeter, you are inserting another dielectric, so that the total 4 millimeter is filled with two dielectrics, not one dielectric, two dielectrics it is filled. Then what is going to be the capacitance of the capacitor? Okay. So what did I do? I just split them into two different capacitors so that you can understand easily and solve it easily. Now for this capacitor, it's completely filled. So what is the formula? You know, epsilon naught K1 by A. K1 is 3. So 3 epsilon naught A by D. D is 2 millimeter in this case. C2 also you can find it in the similar ways. 5 epsilon naught A by 2 millimeter. Now we don't know what is epsilon naught A. We go to the first one information and then calculate what is epsilon naught A. Epsilon naught A divided by D is 2 microfarad. So epsilon naught A will be nothing but 2 microfarad into D. But D for this question is 4 millimeter. So I'm substituting that. So 4 into 2, 8. 8 units are what? Microfarad and 1 millimeter, right? It will be helpful for us to cancel it, right? So here now we come back 3 epsilon naught A by 2 millimeter. Epsilon naught A we calculated it to be 8 into microfarad into 1 millimeter. So I've just written it there. Millimeter and millimeter cancels. 8 and 2 cancel 4 times. So 12 microfarad. In a similar fashion, you find out C2 as 20 microfarad. So it is simply two capacitors whose capacitance are 12 microfarad and 20 microfarad connected in series. That's all. This formula we know how to solve. 1 by C1 plus 1 by C2, which is nothing but 1 by 12 plus 1 by 20. So if you take LCM, you'll get 8 by 60. When you take reciprocal, you get 7.5. Are you clear with this?
Yes, sir.
Yes,
sir.
Now I'm just going to give you some time for noting it down.
Yes, sir.
Can you just see the sum?
Yes, sir.
Yes.
Yes, sir.
Okay. So if you see, it's given a parallel plate capacitor is made of two dielectric blocks which are in series. One of the blocks has thickness D1 and dielectric constant K1, and the other has thickness D2 and dielectric constant K2 as shown in the figure. This arrangement can be thought of as a dielectric slab of thickness total D, which is D1 plus D2, and the effective dielectric constant K, right? Then what is K going to be equal to? Fine. So let's now understand the question here. So I have two dielectrics, dielectric 1 and dielectric 2, correct?
Yes, sir.
Yes. Now, as we did in the previous question, I'm going to split them as two capacitors. Tell me if it's okay with you. Is it fine?
Yes. Yes, sir.
Yes, sir.
Yes.
Yes.
Now, what is the distance here?
D1.
1.
D1 and D2.
Yes. D2. Okay. And we are having a dielectric here, filling this space. And what is the dielectric constant?
K1.
K1. And there is a different dielectric which is here. What is this dielectric?
K2.
K2, exactly, right? Okay. So one of the dielectrics is K1 and the other dielectric is K2. And how are these two capacitors connected? They're connected?
Series.
Series, exactly. Back to back, right? They're connected back to back. So they're connected in series. It's also given in the question itself, right? Now, the question is, if I have to convert this into one capacitor, having a dielectric constant K, and let's say the distance is D, then what will be K equal to? That's the question. Clear? Are you able to understand the question?
Yes.
Yes, sir.
Okay, ma'am. Now, what will be the formula for capacitance in this case? Capacitance will be given by what? If you have a dielectric K fully filling it, what is the formula? Epsilon naught into
Epsilon
A
naught
into A by D.
A by T.
D, correct? So just make a note of that first. Then, okay, this is going to be the formula, correct? Okay. Now let's derive the formula for the next one on the left hand side. Okay. So left hand side you have two capacitors which are in series. So what is the effective capacitance given by? What is 1 by C given by?
1 by C1 plus 1 by C2.
Correct. What is C1 given by? C1 is the capacitance of this one. So can you tell me what is C1? Yes. Tell me.
So epsilon naught
Epsilon naught
K1 A by
K1
D1. A by D1.
K1 divided by D1, correct?
Yes, sir.
The divided by D1, shall I bring the D1 to the top?
Yes, sir.
Similarly, what is it going to be for the next one?
D2 by epsilon naught K2 A2.
A is same. You can clearly see that the cross-sectional area is same, right?
Yes, sir.
Therefore, A is same for both the capacitors. So this is your C2, correct? But what is your C? Already we found the C. What is C?
Epsilon naught K by Ka by D.
So it is epsilon naught Ka divided by D. That divided by D, shall I bring it to the top?
Yes, sir.
Yes, this is the relationship connecting all the three, right?
Yes, sir.
So now what I can do is,
So we can take epsilon naught A and cancel it, sir.
absolutely, we can cancel. We can take out epsilon naught common on the left hand side and right hand side and cancel it, correct? Do you agree?
Yes, sir.
Similarly, A I can take out from the right hand side and that can be cancelled with the A on the left hand side. Yes?
Yes, sir.
Yes.
Yes.
Okay. So what is left here? D by
K.
is equal to D1 by K1 plus D2 by K2, correct?
Yes, sir.
Now let's simplify this further. So D by K will be equal to, if you bring it here, it will be K2 D1 plus K1 D2 divided by K1 into K2, correct?
Yes, sir.
Now let's just cross multiply to get the answer. So take reciprocal first. So K by D will be equal to what?
K1 K2 by
Divided by K1 D2 plus,
K2 T1.
correct. Now this D, can I take it to the right side?
Yes, sir.
Yes. So this will be my result for the K, correct?
Yes, sir.
Yes,
Yes,
so K
sir.
will be equal to K1 K2 into D divided by K1 D2 plus K2 D1. Clear? So which
Yes.
option is correct? And what is D? D is nothing but D1 plus D2. So I can write it here. So K is equal to K1 K2 into D1 plus D2 divided by K1 D2 plus K2 D1. Is it clear to everyone?
Yes, sir.
So which option is correct?
Option C.
Option
Option
C.
C is correct. Now let me just explain it once more, everyone. So a parallel plate capacitor is made up of two dielectric blocks as shown in the figure, which are connected in series. One of the blocks has thickness D1 and dielectric constant K1, and other has D2 and constant K2. This arrangement can be thought of a single dielectric slab of thickness D plus V1 plus D2, and effective dielectric constant K. Then what is the value of K? So you can clearly see the two capacitors are connected in parallel. I just split it up so that you can understand very well. And if this whole thing is made into a combination and the effective value is capital K and the distance between the plates is capital D, small d, which is D1 plus D2, then what is going to be the relationship between K and K1, K2, D and all that, right? So first thing that we can understand is these two capacitors connected in series. So 1 by C will be equal to 1 by C1 plus 1 by C2. And C1 is nothing but epsilon naught K1 A divided by D1. So that by D1 goes to the top. Similarly, C2 will be epsilon naught K2 A divided by D2, which is D2 goes to the top. Similarly, C is nothing but the effective capacitance is nothing but epsilon naught Ka by D. So epsilon naught Ka is here, D goes to the top. Clear? Now epsilon naught A can be cancelled on both the sides. So D by K is equal to D1 by K1 plus D2 by K2. If you take LCM, it will be K1 D2 plus K2 D1 divided by K1 K2. Take reciprocal and move the D this side. So it will be K1 K2 D divided by K1 D2 plus K2 D1. D is nothing but D1 plus D2 as given in the question. So it's K1 K2 D1 plus D2 by K1 D2 plus K2 D1. Is it clear to everyone?
Yes, sir.
Yes, sir.
Very
Yes.
good. Fantastic. Now are you able to see the screen? You can take it down.
Yes.
Yes. And if you have any doubts, just let me know. Should I zoom the screen now or is it fine?
Yes, sir. It is fine.
It's fine? Okay, please take it down. Once you're done, we'll get to the next question. Just give me a minute. Are you able to see my screen? Okay. So let's look at this question. A parallel plate capacitor with air as the dielectric has a capacitance C. A slab of dielectric constant K and having the same thickness as the separation between the plates is introduced so as to fill 1/4 of the area of the capacitor as shown in the figure. What is the new capacitance going to be, right? So are you able to see this?
Yes, sir.
Yes. Okay.
Yes.
Now, if you see, so you have a parallel plate capacitor. The distance between the plates of the capacitor is what? T itself. Now, what is happening is, it is split not in the usual way, all right? Usually we know, right? If we have a capacitor here, you have a dielectric along the length, correct?
Yes, sir.
Yes, then we know the formula for this. Capacitance is equal to epsilon naught A divided by D minus T plus T by K, correct?
Yes,
But it is not
sir.
split like this. How it is split is like this. Are you able to understand how it is split?
Yeah, sir.
Yeah, okay. So this is how it is split. So it is, we don't have a direct formula for this. Do we have a direct formula for this? No, correct?
Yes.
So now let's obtain this formula. Okay, fine. Now just tell me whether I can write this as
Sir?
just tell me whether I can draw it like this. Can you hear me?
Yes, sir.
Yes, sir.
This is the air region of the capacitor. Are you able to understand how I have drawn this?
Yes.
Yes, I have just split the capacitor like this. Correct?
Yes, sir.
And again the connection like this. Clear now?
Yes, sir.
Yes,
Very
sir.
good. Very good. Very good. So what happens is, this is also T, this is also T. Correct? Now, the only difference is, if this total area is A, okay, it is given that 1/4 of the capacitor is filled. Clear? By the slab. Are you able to understand? So 1/4 of the capacitor means, if the total area is A, then what is 1/4 of A? A divided by 4. Understood?
Yes, sir.
Yes. What
Yes,
about the
sir.
other one? What about the area of the other one? What about the area of this region? Total is A. This portion is A by 4. What will be the other portion?
3A by 4?
Exactly. Because the total area is A, that is now split as A by 4 and 3A by 4. Have you understood?
Yes, sir.
Yes, sir.
That's all. So you have all the information that is required for you to solve this sum. So can you tell me the capacitance of air plate capacitor? What is the formula for air plate capacitor? Similar air filled capacitor. Simple capacitor. What is it?
Epsilon naught into A by
Epsilon T into
Epsilon naught
A
into
by
A by D, right? But what is A here?
A by 4 and 3
A by
No, 3 for the air capacitor. What is it?
3A by 4, sir.
Exactly. So in place of A, you should substitute what? 3A by 4. And what is D here?
distance
The distance in this problem is
T, small t.
huh?
Sir.
T.
T, sir.
Exactly. Exactly. So this will be nothing but 3 divided by 4 into epsilon naught A by T. Understood?
Yes, sir.
Yes.
Yes, sir.
Then you have C, dielectric. So for the dielectric, whenever dielectric is going to be introduced completely into a parallel plate capacitor, then what is going to be the formula going to be? Yes, Rebecca?
Yes, dielectric.
Yeah, if dielectric is completely inserted, what is it going to be?
It's epsilon naught into K into A by D, sir.
Very good, ma, very good. So here also it is epsilon naught into K. But what is the area for the dielectric capacitor?
A by 4, sir.
A by 4. Excellent. What is the distance?
Distance is T, sir.
Very good. Excellent. That's all. So this becomes epsilon naught A by T into K by 4. Clear?
Yes, sir.
Yes, sir.
Yes. But the parallel plate capacitor with air as the dielectric, which means with air has the capacitance C. That means, if you look at the first statement, a parallel plate capacitor with air as the dielectric has capacitance C, which means if it is simply air filled, completely if it is only air filled, if it is completely filled only by air, then what is the capacitance given by C in this question? Clear? Then in that case, what is the thickness is anyways T and area of cross section is A. So in this case, what is capacitance C given by? Normal air capacitor, what is it? Aishwarya, can you tell me? Aishwarya is here. No, Akila, can you tell me?
What, sir?
What is the capacitance of the air-filled capacitor? Simply air is filled. Anybody else?
3/4 epsilon naught A by T.
No, not 3/4. Just simply fully air is filled for area A.
Then epsilon naught A by T.
Epsilon naught A by T.
Yeah, epsilon naught A by D. But in this case, D is nothing but T. Are you able to understand?
Yes, sir.
Yes,
Yes,
sir.
Now, 3/4 is what is happening now. But originally, what is given? A parallel plate capacitor with air as the dielectric completely has a capacitance how much? C. Clear?
Yes.
Yes. So now let's look at this now. How are these two capacitors connected? Can you tell me?
Parallel.
Parallel, very good. So if two capacitors are connected in parallel, what is the effective capacitance?
CP is equal to C1 plus
C1 plus C2.
Exactly. So it will be nothing but C air plus C dielectric. Correct?
Yes, sir.
So this will be nothing but, just write it here. So it is 3/4. So can I write it as 3/4 into, what is this epsilon naught A by T?
C, sir.
C, sir.
C itself, right? Exactly. So epsilon naught A by T is C, therefore I can write this as C. What about this one now? K by 4 into what is epsilon naught A by T?
C.
C.
C itself.
So K by 4 into C. Therefore, C air is 3C by 4. What about dielectric? C
K by
dielectric
4.
is
KC by
AC by 4. Exactly. So I can take C by 4 common. So it will become K plus 3 into C. So K plus 3 into C by 4. Which option? First option is going to be correct. Are you clear now?
Yes, sir.
Yes, sir.
Yes, let me explain it once more. A parallel plate capacitor with air as the dielectric has a capacitance C. A slab of dielectric constant K and having the same thickness as the separation between the plates is introduced so as to fill 1/4 of the capacitor as shown in the figure. The new capacitance will be, okay. So if you see, you have parallel plate capacitor with air as the dielectric. That means separately, if only fully air is there, area is A of A, T is the thickness or the width of the capacitor or the distance with the plates of the capacitor. Then what is the capacitance C going to be equal to? Epsilon naught A by T. Now, what I'm going to do is I'm going to make an arrangement like this, where into this, I'm going to insert a dielectric whose thickness is same as the separation between the plates, but area is going to be different. What is the area going to be? It is going to be 1/4 of the capacitor. So if the capacitor has area A, then the dielectric portion is going to only occupy 1/4 of A. That means I have drawn it here, A by 4. So air will be the remaining part, which is 3A by 4. So now I have split it here like this and shown it clearly for you how this capacitor behaves. So it behaves like these two capacitors are connected in parallel. Are you able to understand this?
Yes, sir.
Yes, sir.
Yes, sir.
Then
Yes,
very
sir.
simple simplification. We find out the dielectric capacitance due to air filled in the 3A by 4 area and the capacitance of the dielectric capacitor. So here, if you see, it's going to be epsilon naught A by D. A is 3A by 4 here divided by T. So that's nothing but 3 by 4. I'm taking it common. Then epsilon naught A by T. Epsilon naught A by T is nothing but your C. So I'm replacing it as 3/4 of C. Then inside the dielectric, if you see, it is going to be what? Epsilon naught K into area by distance. Area is nothing but A by 4 this time. So 1 by 4, K by 4 I'm taking out. Then epsilon naught A by T. And epsilon naught A by T is again C. So it's K by 4C. And these two capacitors are connected in parallel. Therefore, the effective capacitance will be simply the addition of the two capacitors. So it's C air plus C dielectric. When you add the two capacitors, you take C outside. So K plus 3 divided by 4. So that's going to be the first option. Is it clear to you?
Yes.
Yes, sir.
Very good. Now
Sir.
you can take it down. Let's give you some time for taking it down. Give me a minute.